Let's look at the next section, 1.5 nested quantifiers. Alright, so this idea of a propositional function we've been looking at. And here's an example with two variables. So this is p of x comma y. Again, this is a function. This is the function notation. So two numbers going in. And then what comes out? Well, what comes out should be true or false, depending on what the numbers are. Okay, so these propositional functions, they're statements about the inputs. And for example, here, p of 1 comma 2, well, if you put in 1 for x and 2 for y, 1 plus 2 is equal to 3, so that's a true statement. But if you put in different numbers, if you put in 2 for x and 5 for y, then this is not true, so that this is false, p of 2 comma 5. Okay, so this propositional function says x plus y equals 3. Yeah, it's not the same as maybe the kinds of functions we're used to. So it's not saying p of x comma y is equal to x plus y. It's a bit different. Yeah, we're used to functions given by formulas, but now we have a function given by a statement like this. Okay, so the main idea is these propositional functions, once you put in the numbers, they have to be true or false. Okay, if you don't put in numbers, then it's not a proposition. If you quantify one of the variables, if you say something like for all x, p of x comma y, it's still not true or false, it still depends on y. But if you quantify both of the variables, then that does make it a proposition, and it will be true or false. Yeah, here we're talking about numbers, say all x and y are real numbers. Okay, so this statement, this expression for all x, for all y, p of x comma y. Okay, so that does make this a proposition. It's saying, yeah, for all real numbers x and for all real numbers y, we have x plus y equals 3. Okay, so it is a proposition, but it's not a true proposition. So x plus y equals 3. That's not true for all x and y. Here's a counterexample: x equals 10, y equals 300.7. So these are two real numbers, so that if you add them, you don't get 3. All right, there are lots of other counterexamples. Okay, so with 2 for alls, we get a false proposition. How about this combination? So for all x, there exists a y, so that p of x comma y. Okay, so we've quantified all the variables, so this is a proposition. And what's it saying? Well, it's saying for all real x's, there exists the real number y, so that x plus y equals 3. Alright, yeah, and so that is true. So if you start with any real number x, then yeah, you can always find a y to make this true. You're just solving for y. If you start with, say, x equals 10, then you need 3 minus 10, that's negative 7. Alright, so for all x's that you start with, you can always find a y. So there exists a y, so this expression is true. Alright, let's switch them. How about this one? There exists an x, so that for all y, p of x comma y, okay, so why is this false? Okay, yeah, don't forget, so p of x comma y is saying x plus y equals 3. So can we find an x? So is there a number we can put here, say 15 or something, so that if you add any real number to it, you get 3? No, so that's not going to work. So if x is, say, 1, then y could be 2, but for any other number, for all numbers except for 2, it's not going to be true. Alright, so this one's false. And the last combination, there exists an x, and there exists a y, so that x plus y equals 3. Yeah, that's true. X could be 1, y could be 2, so there do exist an x and a y to make this true. Okay, so these two quantifiers, the for all and the there exists, they really are different. Okay, example 2, convert this into English and decide its truth value. Again, the domain is the real numbers. Okay, so we have for all x, there exists y, so that x times y equals 1. Alright, so instead of a p of x comma y, we just have the explicit statement. Let's think about this. So for all real numbers x, we're looking for a y, another real number, so that x times y equals 1. You could try to, look at different examples. So suppose x equals 2, for example. If x is 2, can you find a y so that 2 times y equals 1? Yes, so y could be 1/2. 2 times 1 over 2, that's equal to 1. So this looks good. So if you start with any x, the y you need is just the reciprocal 1 over x. Okay, so what's the problem? Are there any issues? Is there any x where we have a problem? Yeah, there is one bad number here. If x is 0, what's 1 over 0? That's, yeah, undefined. We can't divide by 0. So that's the only, yeah, so if you, so this is supposed to work for every real number x, but there's a problem when x is 0. 0 times what equals 1? Yeah, there does not exist another number, a number so that 0 times it equals 1. So this is almost true, but you just need one counterexample to make it false. So this is false. All right, but it was almost true. Yeah, we could try to fix it. So how could we get a true expression? Well, you could say for all x there exists a y so that either x equals 0 or xy equals 1. All right, so this is true. So even if x is 0, then this will be true. True or something will be true. And if x is not 0, then there does exist a y to solve this. Or yeah, more complicated way to make it always true. Yeah, for all x not equal to 0 implies there exists a y so that xy equals 1. Yeah, so this is maybe a clearer, it's more complicated, but maybe a clearer way to say that every real number has a multiplicative inverse. Every real number except 0. So as long as you don't start with 0, then there is some number you can multiply by to get 1. Just the reciprocal. Yep. Alright, so yeah, here we're combining for all with an implication and an existence. Next example, is this expression true when the domain is again the real numbers? There exists x so that for all y 2xy equals 3x. Alright, so we're looking for a real number x so that whatever y is, this is true. Again, if you're trying to figure, try to make sense of this, you could try putting in different numbers. For example, when x is 1, we're getting 2 times y equals 3. Well, that's not going to work for every y. Okay, so x equals 1 is not a good number to make this true. But can you see a number to put in for x to make this left side always equal the right side? Yeah, so x equals 0. So if you multiply anything by 0, that's 0. So if x equals 0, then this is always going to be true. It doesn't matter what y is. Yeah, so this is true. The x that you need is just x equals 0. Okay, some more examples in the book. Yeah, in this section, examples 9 and 10. Yeah, here's a table of what can happen when you're quantifying two variables. Okay, example 9. Yeah, we have two propositional functions here. C of x says that x has a computer, and f of x comma y says that x and y are friends. Okay, the domain here, yeah, it's not numbers, it's all students in your school. So can we figure out what this means? Okay, so for all x, for all students in the school, x has a computer, or there exists a student y, so that y has a computer and x and y are friends. So can we say that more simply? Yeah, it's saying for every student in the school, either that student has a computer or they're friends with someone that has a computer, another student. So this piece here means, yeah, you have, so x has a friend y that has a computer. Yeah, so every student in your school either has a computer or they have a friend who has a computer. Alright, that's the translation. Okay, how about this one? Again, f a comma b means a and b are friends. The same domain. So there exists a student, so that for all students y and z, x and y are friends, and x and z are friends, and y and z are not the same student, and that implies y and z are not friends. Okay, yeah, that's more complicated. So let's read it one more time. There exists a student x, so that for all students y and z, y not equal to z, that first student is friends with both of them. That implies those two friends are not friends of each other. Alright, so I guess, the simplified version is, there is a student in your school who has friends, but all of their friends are not friends with each other. Right, I think that's what they're saying here. So if this X is friends with two other students, Y and Z, then Y and Z are not friends with each other. Okay, so we had an ands here, and then a conditional statement. So if this is true, so if the first student is friends with Y and Z are two different people, then Y and Z are not friends with each other. Okay, now we can go in the other direction. So now start with the English, convert that to the logic. Here's example 4. So this is one of the homework exercises or variation. So this time our propositional function Lx comma y is saying x loves y. The domain, it's a set of people, maybe everybody in New York City. Translate these sentences into logical expressions. Alright, so everybody loves somebody. Everybody loves themselves. There is somebody that loves, that everyone loves. Nobody loves Phil. There is someone who only loves themselves. Okay, so we want to translate these into logic using this propositional function and our quantifiers. Okay, so the first one, everybody loves somebody. Okay, so remember Lx comma y says that x loves y. Okay, everybody loves somebody. So for all x, that's everybody. There exists a y, there is a somebody, so that x loves y. Alright, so this is what we need for the first one. Part B, everybody loves themselves. That's very similar. We just need one variable. So everybody, so for all x, x loves x. Part C, there is somebody that everyone loves. Okay, so there is somebody, so that's going to be there exists. Okay, so there exists an x, so that for all y, x loves y. Is that the right way around? Yeah, I guess that should be the other way around. So we want y to love x. So yeah, it should be a y, there should be an x. Okay, so everybody, that's all the y's love x. Nobody loves Phil. Well, yeah, that's saying everybody does not love Phil. So we need a negation here. So this says x loves Phil. This, with a negation, x does not love Phil. And that's true for everybody. So nobody loves Phil. And what was that last one? There is someone who only loves themselves. Okay, so there is someone, so there exists an x. And what do we want? We want them to love themselves, so Lx comma x. But we don't want them to love anybody else. So any other y, we want the negation, so not Lx comma y to be true. Okay, and we want this to be true for all y's except themselves. Alright, so one way to do this, so there exists an x, so that for all y, x loves themselves, and if x is not equal to y, then x does not love y. Alright, so this is saying x loves themselves and they don't love anybody else. Okay, why do we need an implication? Yeah, it's just this extra condition. So if we need to kind of separate out the condition that where x is where y is equal to x and y is not equal to x. So if y is not equal to x, then we want x not to love y, but we do want x to love themselves. X loves x. Yeah, there is maybe a clearer way to do it. There exists an x, so that for all y, x loves y if and only if x is equal to y. So yeah, maybe this is a clearer way to say that x loves themselves and nobody else. So x loves y if and only if that y is themselves. Alright, I hope you're getting the idea. So maybe this is the more difficult version, so translating English into logic. Okay, and now we negated quantifiers last time. Now we're negating nested quantifiers. But it's the same rule, so we're using De Morgan's laws for negating quantifiers. So if you want to negate for all x p of x, then that turns into there exists an x, so that not p of x. And for negating an existence, that's equivalent to for all x, not p of x. So what happens if we have more than one quantifier? Well, you just keep applying this rule. Example 5. Let's revisit the last example and negate everything. So part A, everybody loves somebody. That was for all x there exists a y, so that Lx comma y. Okay, everybody loves somebody. And now we're negating that. So it's not the case that everybody loves somebody. Okay, so first we negate this, so that for all x turns into there exists an x, and then the not ends up here. And then we have to negate this inside piece. So this there exists y turns into for all y, and the negation moves to the other side. Okay, so the negation starts out on the left, and then we just keep moving it. It keeps kind of jumping over. And every time it jumps, it switches an existence to a for all, and a for all to an existence. So the original negation is equivalent to there exists an x, so that for all y, not Lx comma y. So the negation of everybody loves somebody is there is someone that doesn't love anyone. Okay, so there's some x, so that x does not love any any y's. So for all people, including themselves, x does not love y. Okay, so you can see that's the negation. Everybody loves somebody. Well, the opposite of that is that there is someone who doesn't love anyone. Part B, that was saying everybody loves themselves. Well, the negation of that is there is someone who doesn't love themselves. Yeah, that's easier. And you can try these. How about D? Nobody loves Phil. So if we want to negate this, so it's not the case that nobody loves Phil. Oh well, this for all turns into there exists. this not jumps over, so we get the negation of not Lx. So these two negations, they cancel out, so we get fill. Alright, so the negation of nobody loves Phil is someone does love Phil. There is some X, so that X loves Phil. Alright. Okay, yeah, so we can negate all these quantifiers, yeah, even if it's even if they're nested, even if there's more than one, you can just use these two laws. So in this box, yeah, this is the main thing to remember.